All right, great. So our second talk tonight is from Colin Carroll. He works at a company in Boston called Kensho. The only explanation I got, it's working on fintech. I think he can tell you much more about what they do. Colin is also a contributor to a library called PyMC, which is probabilistic programming for Python. And he's now explaining us what he works on and what he thinks about machine learning and probabilistic programming in particular. So yes, here it is for you.
Thank you. Yeah, so this is going to be a pretty broad talk. I can't imagine there are many talk titles more broad than machine learning and probabilistic programming. And we're going to do this in like 20, 25 minutes. So this is going to be really exciting. And rather than jumping right into it, let me just say, I work at Kensho. It's down the street over in Harvard Square. Feel free to talk to me afterwards if you're interested in hearing more about it. But we do lots of natural language processing there and some fun stuff. Cool. And also before I start, I want to thank, I literally actually reached out to Kaggle. I'm going to use a motivating data set here from their March Madness data set. And I reached out to them and they're really kind in letting me use that. So thanks to them. Kaggle is a data science website. They host a lot of competitions and make a lot of data sources open for people to play around with. So I definitely check them out if you're just looking to get your feet wet with machine learning. Cool, so let's jump right in. We're going to build a model today. I think Jeff was sort of staying out of the weeds pretty well. I'm going to try to dive into the weeds just enough so that we can all ask intelligent questions about machine learning, intelligent questions about the product of models, so that we can engage in discussions and think critically about the models that we're building. And here's some data. This is raw data from Kaggle. The columns are fairly obscure. So the first column here is AST, which is assists, and then blocks. I'm not a huge sports fan, but I am a huge machine learning fan. And over here you can see the team names, whether the team won or lost the given game, what season this is from, how many points they scored. And what we're going to do is we're going to go from there to this model. So the model, and we're being language agnostic here, but essentially you're calling predict, and then you're giving it the name of two teams, so North Carolina and Connecticut. Grew up in Connecticut. My dad went to North Carolina, so I didn't care what the output of this was. So this is sort of an unbiased model. We'll talk more about what that means and why that's an awesome machine learning joke. So the output of this is that North Carolina has some chance of beating Connecticut, and we also get a predicted score. And we want to ask what's going on here. So we might call that previous slide machine learning, but what are we actually claiming is machine learning? So there are two models that are going on. One, I'm doing a regression task. So the regression task, we might have a function called predict scores. And regression means I'm trying to pick some continuous valued number out of an observation. So I'm going to go look up North Carolina, I'm going to look up Connecticut, I'm going to predict a number. So that's what I mean by continuous valued. Under the covers here, I'm actually rounding, I'm getting a float out, but I'm rounding it to be an integer so that it looks like an actual basketball score. It's rare for teams to score half a point. And also, under the covers, there are two regression models. One predicts North Carolina's score and one predicts Connecticut's score. And we're going to talk more in detail about how that works. The other model is a classification model. This is in contrast to regression. All I'm trying to do is put observations into buckets. So in this case, there are two buckets. One is that the first team wins, and the other is that the first team loses, which is equivalent to the second team winning. In other cases, for example, the ones that Jeff was talking about earlier, there could be many buckets, happiness, sadness, or angry. But here we're just looking at two buckets. And so hopefully we'll get through both of these models while we're discussing. Cool. Let me step back. I've been talking fast, but everyone's fine so far. I see some nodding as well. Perfect. All right, so let's talk about model building. We've seen the start of the pipe, we've seen the end of the pipe, and let's see what goes on in the middle here. What we're going to do is we're going to talk about transforming that raw data into features. We're going to talk about how to train this model, what it means to train a model, what a model actually means. Can you pick it up and carry a model around? And then how to evaluate the model. So that'll be sort of questions to ask about models you're getting, how to think about what you've done. Cool. So turning raw data into features. This can be art, science, or magic. Especially with deep learning nowadays, there are ways to do this automatically. what I've done here is I've made sure, first of all, not to peek at the future. The raw data set, if you remember, included the number of assists that the team got in that game, and you won't know that before the game happens. It also includes such really useful features as the actual score of the game. If I'm trying to predict the score of the game, you'd hope the model could just notice that I gave it the score of the game and then output that. So we need to get rid of all this. And so what we do is we turn the features into the average score for every game leading up to the one that we're interested in. So here in this first game, the average score of the team we're interested in, they on average scored 69 points in all games before, but not including this one. We also have that data for the opponent. We have whether it's a home game. This is something I got from just reading literature that home games often matter. That's something that this is why I say it's somewhat art still. If you're really doing feature engineering, you'll want to know something about the subject. I don't know much about basketball, but there's a lot of people have thought hard about it, so you can find this stuff. The other column I want to talk about is these transformed columns. So I think I love linear regression. I think linear regression is really cool. I think it gets a bad rap because of the word linear, and no one wants to talk about linear things. We want like far out features, and we want curves, and we want to capture complexity. And so I want to emphasize that you can do that with linear regression. And so what I'm doing here is on any column that's a percentage, so this is field goal percentage of the opponent. And so the field goal percentage is how many of the shots they take actually go in. And so that's a number between 0 and 1. But really I want to recognize that teams that have a really, really terrible field goal percentage or a really, really good field goal percentage, I should either penalize them or reward them for being near the extremes. And this is somewhat of an arbitrary choice. If you're actually doing this in practice, you would want to try that and try without that. But the way I'm transforming the extremes is I'm putting this through actually the exact same activation function that Jeff was talking about earlier. And so what you can see here is that if a number is over here near 0.9, I'm going to map it all the way up to this curve, and then you can look over, and that's going to turn into a number that's something like 5. So 0.9, I'm going to turn that into a 5. 0.5, I'm just going to turn into a 0. And for negative numbers, I'm similarly going to map 0.1 to like negative 0.5. So I'm taking numbers between 0 and 1 and mapping them to numbers between negative infinity and positive infinity. And so really extraordinary or extraordinarily bad teams will be penalized or helped accordingly for being so extreme. Cool, and that's one way of encoding nonlinearity. Another common way is multiplying two features together. So that's something that you could also pick up. And so you can get actually very curvy models out of linear regression. Great, so what are we actually doing with linear regression? In linear regression, we're making an assumption, and this could be a good assumption or a bad assumption, but we should recognize we're making an assumption that the score of the game is going to be some number times the average score of the first team, plus some other number times the field goal percentage, plus some other number times all these other features. And all we're doing is trying to find all those unknown numbers. So we're trying to fit these W1 through WM in some good way, and we're going to call that our model. And I think this is worth emphasizing that this model, I think I had something like 150,000 data points. Kaggle provides about 13 years of basketball games. It took about 30 seconds to train on my computer, which is a good computer. But the output was just going to be like 6 numbers. So I could write that down on an index card and carry it around in my pocket. And so that's roughly what we mean when we're talking about a model here. Different models have different ways of serializing them. But in this case, there's massive computing power and then just a little tiny bit of output. And then we'll just remember that little tiny bit of output and we'll be able to use it to make predictions in the future. Cool. And so now, we were talking about not doing math, but I really like linear algebra. So we're going to do some linear algebra. This is the fun part for me, and hopefully everyone else will smile a little bit too. So this slide's saying the exact same thing that the previous slide said. So here, this y is going to be our labels, the x is our data, and the w is our weights. And so linear algebra is just the right language to use to talk about something like linear regression. And as an aside, I'm talking about linear regression so much because it's important for many, if not all, machine learning models. Let's say many. many machine learning models. And so I think understanding, at least at a surface level, linear regression is going to help us a lot in talking about a lot of machine learning. And what does this look like in practice? So I actually fit a model here. It's not a good model, and there are a lot of warning signs about this model that will make you think that it's not a good model. One of them is how big of a negative coefficient there is on the opponent's average number of wins. It looks like that number matters a ton, and intuitively we wouldn't want to say that in our story. But roughly, what this model is saying is that for every point I've scored in previous games, I'm going to score 0.6 of a point here, and for every point my opponent scored in previous games, I'll score 0.3 of a point, right? And so if you're looking at any single game, you can go look up all these numbers for the two teams that are playing. You can come out with a prediction for how many points the first team is going to score. And I should emphasize in this picture, the predicted score first is going to be that y variable. That column of numbers is w, so that's what we fit with our model. So those, 8 numbers are our model. And then the numbers on the right-hand side are x, which is our data. Yeah?
Over what time frame are you averaging? over the season up to that point? Or?
Yeah, and I threw out the first 5 games. I would love to have heated discussions afterwards about the model building here. I think it's not very good, but the contest is open, and so everyone can build a model for this before the turn.
And you can't predict the first 5 games of a season?
Not with this model. It's hard to predict with no data or small data. There's much more higher variability. Yeah. Any other questions about this so far?
The curve that you said, is this a part of the W, or is it something that you create while building the regression model?
Yeah, good question. So arguably, when I said W is something I could write on a note card, you also have to remember all the transformations you do to your raw data. And one of the transformations is putting it through this nonlinear transformation. And so this is not part of...
Do you as a human decide this, or do you also get this out of some output while you are training the data?
This one in particular is something that a human gets, or that a human just decides randomly. You can make it so that there are coefficients controlling this, parameters, we would call them, controlling this, that would be set automatically. But in this case, I'm just arbitrarily scaling my variables. Cool. Good questions. Yeah, one more.
Two quick questions.
Sure.
Your equation or the model that you built, there were many variables.
Mm-hmm.
One, how do you sort of how do you build a model which has like finite or certain sustainable number of variables? And second, if say you want to predict, and if you only have data which speaks to say 2 or 3 of those variables, not that entire list, like are we then compromising on the accuracy? What are the trade-offs there?
I think so. The second question I think I'll get to later, and the first question I'd say there's a lot of iteration, and so you'll want as a working machine learning engineer, you'll want to be able to iterate quickly on your model building and be looking at how accurate everything is. And I think I'll talk a little more about how to judge accuracy and how to deal with sparse data. Cool. So let me. Great. So. What can we say about linear regression? I think I led everyone to believe that the W that I chose in the previous slide was somehow a good W, and I want to talk more about that. So I was a pure mathematician in my previous life, and so we don't deal with numbers that dirties our hands. But so here are 3 equivalent statements about the weights that we got out from linear regression. And so the first one, I think this is the most common one when people are talking about linear regression, which is that the weights minimize the sum of the squared errors. Right, and so here you can see in red highlighted are the predictions that we're making. So we pick a W to make those predictions as close as possible to the Y's. And the Y's here are going to be the labels that we get. Right, and so this, if you have any memory of calculus, this is a nice differentiable function in W. You can take derivatives, you can set them equal to 0, you're in a happy space. But yeah, so essentially we're picking a W and we're saying a W is good if it minimizes this equation. And there are lots of reasonable questions you can ask about this equation. Why is it squared? Why is it, why do we care that it's, that it's the difference of these two? Why not the difference of something else? And there are, in fact, other common error functions that people will use. But one reason to use this is that it's exactly equivalent to this statement. So this is a statement from a Bayesian context. This is one that I really like. The equation looks pretty complicated. I think the human sentence below is much more readable. And so this is just Bayes' rule. And it's saying that we're maximizing the probability of seeing our weights given the data. And so that number on the left-hand side is hard to compute, but the number on the right-hand side is easy to compute if we make some assumptions and make them clear. And so this number on the right-hand side is the probability of our data given our weights times the probability of our weights. And so that's our likelihood times our prior. And so we would make those two assumptions explicit, and then we just pick the weights that are the most likely to occur. And this is really nice intuitively because this, we want the most probable weights, and here they are. We're sort of using statistics to get the most probable weights. Cool. And the third equivalence statement, so we had one sort of calculus-y statement, we have one statistical statement. The third one's geometric, and I don't see it used that much in any literature, so I'm just going to sort of put it up here because it's a beautiful picture. It's really nice. It's from linear algebra, but I wouldn't worry too much about this unless you're taking a course in linear algebra now, which I'd highly recommend. But this is just a nice picture. There's in our actual data set, we're in like 150,000 dimensional space and projecting down up to like 22 dimensional space. It's wild. Cool. So those were some equivalent statements of this W. So we got a W that's very likely, and we got a W that's minimizing error. And so what other guarantees do we have about our W? We have these three guarantees. One is that if we have a very easy model, in particular that the model is exactly correct, and so our data was actually generated from the model that we wrote down, we'll get exactly the W that was used. So a concrete example of this is, suppose we get a lot of bills from restaurants, so we know how many of each item someone ordered and their final bill. We should be able to exactly recover the prices that were on the menu. Right? People aren't adding in some random variation to those prices. And so in this case, which we would consider sort of an easy case, there's no noise, there's no error, we exactly know how the prices were generated. We should be able to recover the prices on the menu. And it's reassuring that linear regression tells us we will recover that exact number. The other two are a little more, I think, esoteric, but important to talk about. So one is that there's only one set of weights that will satisfy this. And I've got this big asterisk here. So people who like to talk about counterexamples, we can talk about counterexamples afterwards. But in a reasonable set of data, there will only be one W that satisfies this. And that's nice. When you're training a neural net, there might be many different valleys that are exactly as good. And so two different people training the same model on the same data might end up with two different sets of weights at the end of the day, which is sort of theoretically unsettling. In the case of linear regression, we're not as worried about that. The other is that a set of weights exists that will be most likely, that will minimize the sum of the squared errors. This is nice because you might be sitting worrying one day that maybe if I weight field goal percentage higher and weight the opponent team score lower, I might keep getting a better and better fit, and I keep moving those two numbers bigger and smaller, and the fit keeps getting better and better, and then there's no best model, right? Those two numbers just run off to infinity. But luckily, because math works, that doesn't happen. So good news. I wanted to talk about evaluating our model a little bit. So one good question to ask is, how wrong am I going to be? And so here I've just created a plot of the residuals. Residuals meaning exactly in this equation, I'm plotting the predictions minus the labels. And I'm just going to plot the absolute, or not the absolute values, the actual number there. So you can see how often we're off by, most of the time we'll be off within 20 points of the actual score. I don't know if that's good or bad. I wouldn't go to Vegas on this. If you ask me how much Delaware State and Monmouth are going to score if they're playing each other, I would rather go to this model than guess off the top of my head. So this is something to look at. My wife is a statistician. She told me that I have to tell you that just eyeballing this to see whether this is a normal curve is not good enough. There are tests you can do. There are good tests you can do, and so you should be a careful statistician and not just eyeball things and say it looks pretty normal. So that's something to look at. Cool, and the last thing I want to talk about, and this will address sort of the sparsity, is we might have a data set that looks like this. So this looks visually like a line with just a little bit of noise, and being really enthusiastic about getting low error when I'm fitting my model, I go ahead and I fit it with a 25th degree polynomial. It does awesome, right? It's hitting just about every single data point there. Very low error, much lower error than using a line. But we can all sort of see intuitively that this will do a terrible job if we get a new data point, especially if the data point's over like 0.9 or something, right? That's going to be way off. And so don't have the time, and there's also very good write-ups and videos. Andrew Ng's Coursera course does a great job of going over cross-validation and testing. But I wanted to at least say these words because I think it would be very bad if I did not say the words overfitting and then cross-validation and testing. So you should not be only testing your model on your data set. You should hold out some data to do that. Cool. Any other questions about linear regression before we go on? Actually, we can also talk about that at the end. Yep.
So initial set of values you assume for W weights.
So in this case, and so I used Python to fit all of this, and sklearn actually uses an analytic solver, and so you can just do this exactly. You don't need to. Cool. Yeah.
Is there any objective way to know if you're overfitting? I mean, it seems to me that you would never know because you don't have the next data set.
Yeah. So depending on how big your data is, there are good ways of looking at whether you might be overfitting. There's a beautiful picture of your error going down closer and closer to zero as you add more features, whereas your cross-validation error is suddenly shooting up at some point. And so there's a quick Google search of cross-validation will find that picture, and it's awesome. Great. So let me just talk briefly about logistic regression. The rest of this will be sort of a survey. So logistic regression is confusingly has the word regression in it, but it's a classification algorithm. But it has the word regression in it because it's so similar to linear regression. So you can see here on the left, linear regression is just this nice matrix form, and then logistic regression is just that nice matrix multiplication, but inside a function sigma. And again, this sigma is the same sigma that Jeff was mentioning earlier. And so here's the equation for it, which is nearly as obscure as writing down just the sigma. But here's a picture of it, which is a little bit nicer. And so this is sort of doing the inverse of what we did before, where we're going to take numbers between negative infinity and positive infinity, right, which linear regression will give us, and we'll just plot them back onto the interval between 0 and 1. And so we're going to use this sigma, plot linear regression back to between 0 and 1, and we're going to try to fit a line so that really big numbers are given to events that are very likely to occur, and really small numbers are given, very negative numbers are given to events that are very unlikely to occur. And so this is all logistic regression is. And so a lot of the techniques that we used for linear regression can also be used for logistic regression. And so just want to give one famous example of when logistic regression was used. This is the Challenger disaster. So this is a picture of Richard Feynman, and he's dropping some O-rings into some ice water at a congressional hearing. And he's doing that in support of this data set, which was from various testings of the space shuttle. And you can see I've plotted the points at 1 if there's problems with the O-ring, and at 0 if there are no problems with the O-rings. It turns out so O-rings are like gaskets. If they get brittle, it's very dangerous, as we saw with the Challenger. Right, and you can see here visually that you'd like to fit some sort of S-curve where on the right-hand side you're very safe and on the left-hand side you're very unsafe. And it turns out the Challenger went off when it was, I think, 30 degrees, right? So it's another 20 degrees off to the side of this chart. And so this is one famous example of where people have since used logistic regression to assign a probability of safety for O-rings to launches. Great. And I want to finish with just a quick advertisement for probabilistic programming. So I think linear regression is a pretty, it's, as I said before, it's an algorithm that you can use to help you understand a lot of different machine learning algorithms. I think probabilistic programming is something that's up and coming. I think there's a lot of interest in it right now. So PyMC is the library that I work on, and we just had our first stable release after 5 years of development. So I'd encourage you to go check that out. It's under very active development, so we're accepting pull requests and issues. People respond very quickly, so check that out. There's also these 3 libraries which do similar things. So this is STAN, which is Andrew Gelman's group down in New York. Edward is with David Bly's lab, I think also in New York. And then MC is a useful thing. I think it does less than Stan Edward and PyMC, but it has just this awesome tagline, the MC hammer. So you have to include them. Also, Fast Forward Labs just released a great sort of handbook on probabilistic programming. I've linked to that in the talk notes. And just as an example of what it does, the idea behind probabilistic programming is that we should just explicitly write down our model, our assumptions, hand it some data, and tell it to give us some likely outputs. And so that's what I'm doing here. The Python code looks eerily similar to what I've written up here on the top line. And then down here, you can see I sampled 500 lines that might be likely. This one down at the very bottom, that's where it got initialized. So this is a more iterative algorithm where we'll keep sampling from this probability space. And so you can see it started down here, it walked up to areas of higher probability, and then it just starts sampling from areas of higher probability. So it got into a pretty good mode pretty fast. And once you do that, you get all these estimates on what all your variables are. And so you get a full posterior on all the variables that you put into your model. And that can be very helpful for explaining your uncertainty and explaining how what a reasonable model is and what an unreasonable model might be. So you can see here, it's all the modes are centered right around what they really were. Great. So thanks so much for listening, and happy to take any questions.
So as we think of different problems that we can solve with AI in regression, do you have any guidance or rules of thumb of how we know when we're going into it, whether there's a good chance that we'll get a good result at the end, or is it just trial and error?
Yeah, really good question. I think, so traditionally the thinking has always been that the question is how can you tell when a problem that you might address with AI might come out with a good solution. And I think traditionally you say if a human expert could do it well, then you could probably train a model to do it well. And the idea is that they will likely be using some rule system in their head, and you can learn the weights that go into that rule system more or less. I think now there are beginning to be examples of places where computers can do awfully well. I think of a lot of vision tasks and like diagnosing like certain retinal cancers, which seem almost magical. Which is not a word one should use too much in AI, but I think it's still a reasonable rule of thumb to think if there's a human expert who can do it well, then you should be able to translate that into a machine learning test. Yeah.
Do you think it's possible in the future that you'll have machine learning analyzing machine learning like decisions? Like let's say you decide like certain things. Do you think it's possible that they could be automated also?
It's So the question is whether machine learning could supervise machine learning, and I think that's a really hard question. I think certainly, so everything we talked about today was supervised, which meant I had the labels. Jeff was talking a little bit about this before, where having unlabeled data is much harder. And so you're not sure what the clusters are. And in fact, a lot of the NLP I do has some unsupervised clustering of text documents. And so you'll get a bunch of keywords, and you really want to say, this is like all about, I don't know, phone releases or something, but that's a really dangerous game to start playing because I think a lot of AI can end up looking pretty stupid if you let it run too much amok. So I think definitely not right now, but it's very hard to guess. Yeah.
He was alluding to is at some point we were talking about general intelligence. Sure, like supervised or unsupervised machine learning models are one thing, but we come pre-configured with a neural network, physically neurological network that has the ability for general intelligence. And if we're interacting with our environment, we are trained over time, we learn. So I would think there's no reason why you couldn't, because POC is right here in our heads, but maybe, I don't know, it would take a lot of engineering, and it might be very dangerous to have random general intelligences walking around doing something. So, you know, I don't see any reason why not, but it would be difficult to take a long time. So, and do we want that? I don't know.
Sure. Yeah.
I have a question. So you have the Bayesian analysis, and then you also can do the regression like on all the data. So in which case you use the Bayesian regression, and in which case like you load all the data and run it?
Oh,
Practice or
yeah. You typically use an MCMC sampler like PyMC in cases where it's unfeasible to calculate the posterior distributions by hand. So this is really what you're looking for are these posterior distributions. In cases those are intractable to compute by hand. So in this particular case, you could do this by hand. So it was sort of in some sense pointless to sample like this here. But there are more complicated models you might put together with many different layers where it would be harder to calculate these exact distributions. So I think you try doing it by hand because it's much faster and much easier for the computer. If that proves impossible, then you would move to a tool like this.
when you say by hands, like what do you mean? I thought like we can just load the data and it's run it and.
Yeah, so most linear regression software will not give you estimates on these posterior distributions. So it's essentially at some point you have to do an integral, and that can be hard to do with a computer. And so MCMC seeks to do that faster and more efficiently with a computer. So that's roughly it. So by hand, I mean like calculate the integral by hand.
Maybe one more.
Yeah.
So Colin will also be around after the talk. Maybe take one more beside.
Sure.
Hi. So I had a question on PyMC.
Sure.
If you want to run PyMC, but you also want to give an additional constraint that the magnitude of the weights has to be, say, natural, less than 10 or something like that, is it possible to do that in PyMC?
I don't believe we have linear constraints or any sort of constraints like that. You would probably again have to work something out by hand and use some other methods. But.
So I mean I'm going towards ridge or lasso kind of regression, right? So
Ridge or lasso, you certainly can. I mean those are putting priors on some of your parameters.
okay.
Yeah. Great. Well, thank you so much. I'll